All right, welcome back, everybody. This is William M. Briggs. We're on episode 22 of Uncertainty and Probability Theory, the Logic of Science. This one, welcome to the Continuum. We are now going to introduce our very first infinite dimensional probability space. We've been working with discrete things all along, and in the end, we're going to end up working only with discrete things. And we're going to discover today that the continuum is only an approximation. Very useful approximation many times and oftentimes, but it is only an approximation, as I hope to demonstrate to you. We're going to continue on Jayenes. Last time we did some elementary so-called hypothesis testing, where actually all we did was form some proposition of interest about some things we wanted to know about, made some assumptions to start with. We took some observations about some bad widgets, and then we calculated the probability that we were dealing with a machine that produced a certain level of bad widgets. We assumed in that particular example that the number of bad widgets came out as the worst one is 1 in 3, and the better ones is 1 in 6. Well, now let's introduce a parameter that can take any value. We'll just say it's any value in the continuum. Any value that's going to, in this case, be a positive value, because this is going to be the proportion of bad widgets. So f could be any number between, it could be any number between 0 and 1, because this is going to be the proportion of bad widgets. We don't know what it's going to be, but we want to make some probability of any particular number that it might be. All right, so we could define, just to show you how this stuff originates in the most natural way using the probability rules we already know. We don't need any fancy mathematical apparatus like this. We can define this, whoops, let me just erase that there. We can define this f prime. We're going to define it as, say, f is less than or equal to some q. And we could even define some f double prime, I did it again, as equaling some f greater than q. Notice the lack of the equal sign there. These are, depending, of course, if we pick the right q and everything, these are mutually contradictory, or rather exclusive propositions and everything. We can certainly calculate probabilities of things like f prime, and we can calculate things like f double prime using all the rules we've already learned. Okay, we can write out a function. We can call this function g. Evidently, it'll be a function of q. Q is just some number we could pick in this interval 0 to 1. And it will be defined as the probability that f prime is true, given, what did we use for background information? Y. It doesn't matter. We have some background information, and that tells us that, I think we used x, but Jayenes uses y here to differentiate it. It's a different problem. This is giving us some information about the machinery that we're dealing with and the observations we're going to take and all this kind of stuff. We can certainly calculate this probability. No problem. So, but what if we wanted to know? What if we wanted to know the probability that f was going to be between some values? This particular fraction of bad widgets is going to be between some values. Well, let's calculate this. You're going to know the answer. It's going to be obvious. You probably already guessed the answer and all this kind of stuff. But let's work through using the simple rules that we have deduced so far to show you that there's no magical trickery happening here. And then to make a very serious point about infinity, which I warned us we're going to meet again. So we could define, just define this proposition A as f being less than or equal to some A. And likewise, we could define this B being f being less than to some B. And we could define W as being A being in this interval. What do I wanted to do up here? I wanted to keep, got to be strict about these things. Okay. Well, I want to know that f is between A and B, and this is what I have here. So I have just 3 propositions. This makes perfect sense. This makes perfect sense. This makes perfect sense. And if I have real widgets and I'm measuring real proportions of bad ones or good ones or whatever I'm measuring, I can observe these kinds of things. I have certain assumptions here. I can calculate probabilities of all these things. Remember, probability is just the relation between propositions, evidence that I assume, a proposition of interest or a hypothesis, whatever you want to call it, and all the things I assume about it. All right. Well, evidently from this, we have that B equals, make sure I have my notation. Yeah, A plus W, that makes sense. Let's just make sure I have this. A plus W. A is everything less than A, less than or equal to A, and B is less than or equal to B. So make sure I get all my inclusions exactly right. So B is A plus W. No problem there. Okay. So now let's calculate some probabilities. I need, unfortunately, there's only a lack of board space, but this is not a very complicated derivation. I think that anybody who's got some math under them has already seen the answer, but it's still worth going through, I think. So we can calculate the probability then of B given Y, and that's just going to be the probability of A given Y plus the probability of W given Y, simply because of these facts. No problem, because we're using Boolean algebra here. This is Boolean algebra. B is the Boolean logical addition of these two sets right there. No problem. So there we go. So now what we could also know, the probability of B given Y is going to be G of B. And the probability of A is going to be GA, no problem so far. And the probability of W is going to be GB minus GA, no problem there. Now, here comes the big move. Let me get rid of this. Right up here, buddy. Here. Greedy is back. He's still camera shy. He doesn't ever come up here when I'm on the board. So if we assume that function g is continuous and differential and all that kind of standard stuff you remember from analysis calculus and all that kind of stuff, if we assume that that's going to be the case, then we know the probability that of what we're after, f is between a and b given y, is going to be, it's not a mystery here, it's going to be g of f df, where g of f equals the derivative of our function g. Now, okay, that's a lot of work just to get the probability that f is going to be in some interval. This is now called a density. It's not a probability, it's a density, because we're assuming this is continuous, meaning on the continuum, it's a real number, f is going to be a real number, and differentiable and all that kind of a thing. It makes for a very handy way to make these kinds of calculations, especially when we can write, some of these functions are going to turn out to be very nice and analytic, meaning we could write them out, we could solve them very simply, or they're not analytic, but they're still well behaved. We can handle them numerically, all kind of numerical approximations and all these kinds of things. Makes the math easy, especially if you're doing, and probability is mathematics in a certain sense. Probability is, you can go to town with probability as mathematics, proving all kinds of theorems and so forth. But again, here's the point. Once we try to apply these things to real life, and f is going to be a real life thing, and in this case y is real life assumptions about real life we hope are true, or at least assume are true. So we can make things like this. This is a density. It's not a probability. It is a density. You've seen pictures of, for instance, normal distributions. This is not a distribution of f. We're going to use this here. It's not of f. It is a this thing right here is a probability for f, not of f. F does not have a probability. Nothing has a probability. How many times have I said this? Nothing, no thing has a probability. We meet many, many instances of the deadly sin of reification here when people try to speak of the true probability of F, and they'll call this creature right here, this density, as if it has it. You've seen pictures of normal distributions, for instance. Well, that is a density. It is a density for a certain observable. And F is going to be an observable in our case. We're calling it a parameter in a loose fashion. Later I'm going to call parameters only those things that are unobservable, and we'll write them by Greek letters and so forth. But this is not itself a probability. It is always incorrect to speak of it as a probability. It is a density. It is just a function. It's just a simple mathematical way to write this. We don't know what this the original G function that we had, that may have some mathematical form that we're assuming or using. There you go. You know, and so we could, if we could take the derivative of it, we could write things like this, and we can go to town using our calculus and so forth. No problem about that. But this is just a mathematical representation of the density of it. This entire thing, again, this entire thing, this is the probability. This is the probability. This is not the probability. This is just some mathematical apparatus that lets us calculate things easier. Now, we have assumed here that G is continuous and differentiable and all this kind of a thing, thing, thang, thunk. But in real life, what do we have? We have a machine that's spitting out. We're assuming these are. We're assuming these things are defective widgets or something like this. So no matter how many times this machine has run, it's going to run a finite number of times. It's going to spit out a finite number of widgets that in real life will be less than infinity. There's absolutely, and that the probability of this statement is true given everything I know about infinity, which is to say nothing that we have produced can be infinite or anywhere close to infinite. Any number of things that we produce is always infinitely far away from infinity. We'll always have a finite number of widgets that this machine can produce, even if it lasts for thousands of years and is spitting out widgets 1 per second. Doesn't make any difference. N can be as big as you like. And remember, we did that one lesson, I forgot the number of the class, where we have N using tetrations and so forth. We can imagine or write down numbers that are N or that are unimaginably, I can't imagine them, unimaginably big, but they're still an infinite distance away from infinity. So there's no loss of knowledge or no loss of precision by assuming N is finite. So what we really have is we're going to have some fraction, will be 0, some fraction of bad ones. It could be 0, but F1 could be bigger than that. F2 could be bigger than that. F3, we're just imagining these real life fractions. It'll be F, N, which will be less than or equal to 1. Where each Fi is going to be the number of bad over N. Number of bad up to up to number of bad. Well, that's it. That's exactly what it is. Number of bad that we're going to have somewhere. F is going to be one of these numbers, is the point. F is going to be some real fraction, the number of bad that we really get over however many that we're going to have. And if N is large, and that's a relative number, remember, compared to infinity, it's always infinitely small. But practically speaking, in decisions that we make about things, which are different, this is a different thing now. Decisions are not probabilities and so forth. We always got to keep this in mind. So a relative sense, and that's problem dependent. It's problem dependent. It depends on what we're going to do with this information about F, all that kind of stuff. So there is no fixed number that means large. It depends on you, it depends on the problem, it depends on the widgets, depends on the machines, depends on the decisions you make about it, depends on the probability you get out of all that kind of stuff. There is no fixed definition of large. But for N large, for you. This approximation, where we assume it's a continuous function, may be absolutely just with ease. I mean, the mistakes that we're going to make by assuming, and it is a mistake, all approximations are mistakes in a rigorously formal way. But if we assume some, continuous function that's close enough to all this kind of a stuff for the f's that we're going to see for this particular machine, we might be able to get away with just making our life easier with calculations and so forth. Absolutely no problem to do that. None whatsoever. I am not disputing the math. I mean, this math, a lot of this math is absolutely useful and wonderful to have, all this kind of a stuff. But it is always an approximation. This is not life. This is life. We have this right here. We always have to remember that this is an approximation for this. And this is only the derivative of this, which is an approximation for this. So we're getting further down the road from reality. And later we're going to see things like this. I'll just give you a little teaser right now. Later we're going to have things like this. We're going to say this GF is going to be some function itself that's going to have, I've already used it, maybe I'll use H. It'll have parameters, Greek parameters in it that are unobservable, absolutely, but allow us to make these, an F. I guess I should stick an F in there, that allow us to mathematically manipulate things like this with ease, as long as we stick in some values of parameters for them. We're already gone past real life now. We're 2 levels down from real life, and when we add this kind of a stuff, however advantageous it is to us, and there's lots and lots of advantages, that has nothing to do with the way the world is. Even if space itself, yeah, here we go. Even if space itself, and I'll try to draw the real line here, even if space itself, this is my metaphor for it, is itself continuous, absolutely continuous along the continuum, that level of infinity that we all meet in analysis. And if you don't understand that, don't worry about it right now. Anything that we could know about this, unless it comes from metaphysical principles or something, anything that we can measure about this, I should say, anything we can measure about this will be discrete and finite. That's it. We're stuck with discrete finite machines. No matter what else we have discrete finite machines of every measurement we ever take. Of course, when we're dealing with large, again, in quotes, large numbers of these measurements and so forth, it's very useful to use this apparatus. But that's all it is an apparatus. We will not, in this class, make the deadly sin of verification. We're going to avoid it at all costs. And I'm warning you about it now, and you'll think, oh yeah, I'm never going to do that. I understand the difference of all this. It makes sense. But once you start doing this stuff, these equations really do come alive, especially when you're submitting it to software and out pops these nice answers and so forth. And then you're very tempted to say, this is the probability of, instead of a representation of something for, as an approximation. So life, I'm going to emphasize this stuff again and again and again, is purely, for us, in our knowledge anyway, except for certain metaphysical principles and so forth, and universals and all these kinds of things, where we do jump to infinity. But we're in science about observables. When we're talking about observables, life comes down to measurements, and all of these are always discrete and finite, even if large. Okay, that has to be kept in mind. So we could use all this, and it's no problem. But the neat thing about this was, and Jayenes makes this is his chapter 4.6. You'll see in the notes, this is what you're supposed to read and do. The whole point of doing it in the way we did it today was to show you that all of this continuous mathematics and everything comes from these very simple assumptions that we made, everything we deduced about probability to this point, that it can be a function, that it's Bayes' theorem is the mathematical form of it, that we can assign numbers from the symmetry of logical constants and all that kind of a stuff, and we move forward with all various sampling distributions, all this kind of a thing. All of that stuff was discrete and finite, This stuff arises from discrete and finite assumptions just because of the way we defined this particular function. And all of it works. We don't need to jump right to the most complicated mathematics as a lot of books and things like that do. We could, as long as you're aware of what you're doing, but the problem of making a mistake and getting in more and more depth, down we go, farther and farther from reality, the more difficult it will become for you to remember where you are and what your purpose was when you're doing this. And I promise you, we're going to come to many more examples of this. Right now, that's basically it. We're going to, next time or a time after, we're going to use this for more hypothesis testing. We'll continue with Jayenes and show what he does with this level of stuff and how useful that can be. And then we'll start talking about chance and randomness. And I think that's going to be a really arousing discussion, at least for me. I think it's a fascinating topic. I hope you like it too. That's it for now. More information is down below, and I'll see you next time.